How we avoided extinction. The sky above the East African plateau is pale and enormous, a vast dome of white-blue stretching from one flat horizon to the other. The grasses below it are golden and brittle, cracking underfoot, and the acacia trees that dot the landscape are scattered wide apart, throwing patches of thin shade across the cracked earth. A group of small, upright figures moves through this landscape at a careful, deliberate pace. They are not large, not by the standards of the time, and they carry nothing but sharpened stones and the memory of a watering hole 3 hours to the north. One of them, a young female, pauses and turns her face into the wind. Her eyes scan the middle distance. Something is moving out there beyond the shimmer of the heat. She makes a sound, not quite a word, but something more than a grunt, and the group coalesces instantly, shifting formation without debate or ceremony. Whatever is out there changes course. The group moves on. We do not know this female's name, of course. She left none. No grave, no monument, no inscription in stone. But she is part of a chain of individuals stretching backwards in time for millions of years and forwards to every human being alive today. The simple act that she performed just then, communicating a potential threat and prompting a collective response, is part of the reason that you are here to read about her. Because survival, it turns out, is rarely about a single dramatic moment of triumph. It is instead the cumulative product of 10,000 small advantages, exercised over millions of years in a world that was doing everything in its power to end the lives of the creatures that lived in it. This is the story of how we survived. Not just the last ice age, not just the spread of our species out of Africa, but the entire staggering, improbable journey from a small primate in a shrinking forest to a civilization of 8 billion people. It is a story about climate, about competition, about cooperation, about the fine line between adaptation and extinction. And it begins, as all the best stories do, at the very edge of catastrophe. To understand just how unlikely our survival really was, it helps to understand quite how many times the conditions for that survival nearly ceased to exist. The Earth is not a stable platform. It never has been. Over the last 65 million years, the period since the asteroid impact that ended the age of non-avian dinosaurs and inaugurated the age of mammals, our planet has cycled through periods of extraordinary warmth and extraordinary cold, of lush global forests and near-barren glacial wastelands. Species have risen and fallen with these fluctuations like boats on a tide. Most have sunk. The primate lineage that would eventually produce us emerged in a world dramatically different from our own. The early Eocene epoch, roughly 50 million years ago, was warm enough for forests to grow within the Arctic Circle. Primates at this time were small, tree-dwelling creatures, their anatomy shaped by millions of years of life in the canopy. Grasping hands, forward-facing eyes, brains slightly larger in proportion to their bodies than other mammals of comparable size. They were successful and widespread, distributed across the northern hemisphere from Europe to North America to Asia. They were also, by any reasonable measure, utterly unremarkable. Nothing in their early history suggested that one branch of their family tree would eventually produce creatures capable of language, art, mathematics, or space travel. But the history of life on Earth has a way of producing the extraordinary from the ordinary, given sufficient time and sufficient pressure. And pressure, over the next 50 million years was something the primate lineage would experience in almost unimaginable quantities. Between 10 and 20 million years ago, during the middle portion of a geological epoch called the Miocene, the world was in many respects a paradise for our ape ancestors. Global temperatures were higher than today. Tropical and subtropical forests covered vast portions of the globe, and the ape family, which had diverged from its monkey relatives in the early Miocene, was experiencing an extraordinary flourishing. Dozens of species of ape ranged across Africa, Europe, and Asia, from creatures no larger than a house cat to behemoths that would have dwarfed a modern gorilla. This was, in the truest sense of the phrase, a planet of the apes. And yet, even in this golden age, the seeds of future disaster were already being sown. The earth was cooling, almost imperceptibly at first, but with a momentum that would prove impossible to arrest. The causes were multiple: shifts in ocean circulation driven by the movement of tectonic plates, changes in the composition of the atmosphere, the gradual growth of ice sheets at the poles, and the effects were slow but cumulative. Decade by decade, century by century, millennium by millennium, the forests that covered so much of the planet began to contract. The great green canopy pulled back from the high latitudes, retreating toward the equator, and in its wake it left something new. Vast open grasslands, sweeping savannas. Landscapes dominated not by trees, but by grass and sky and distance. For the majority of the Miocene apes, this change was catastrophic. They had evolved to live in forests, to swing through canopies, to feed on the fruits and leaves that forests provided in abundance. When the forests contracted, their food supply contracted with them. When habitats shrank, competition intensified. Species that had coexisted by occupying slightly different ecological niches, a phenomenon called niche partitioning, by which different species avoid direct competition by exploiting different aspects of the same environment, now found themselves competing for the same dwindling resources. One by one, and then in waves, the Miocene apes went extinct. A family that had numbered perhaps 100 species dwindled to a handful. This was the Great Pruning, and our ancestors survived it, though only barely, and only because they possessed qualities that most of their relatives lacked. One autumn morning in 1974, a team of paleoanthropologists was working a remote site in the Afar region of Ethiopia. A landscape so stark and sun-beaten that it seems barely capable of supporting life. Donald Johanson, a young American researcher, was heading back to camp after a fruitless morning of surveying when something caught his eye. A fragment of bone, small and brown, jutting from the eroded slope of a ravine. He paused. He crouched. He looked more carefully. And over the next several weeks, he and his team would uncover 47 separate fragments of a single skeleton, pieced together on a makeshift table in a camp tent, to reveal a creature unlike anything previously described in the scientific literature. She was small, just over a meter tall, weighing perhaps 29 kilograms, and she had lived approximately 3.2 million years ago. Her legs and pelvis were shaped for walking upright on 2 feet. Her arms, however, were long and curved in a way that suggested she was still comfortable in trees. Her brain was small by modern standards, little bigger than a chimpanzee's. She was, in every sense, a creature caught between two worlds, between the ancestral arboreal life of the ape lineage and something genuinely new, something that was only just beginning to take shape. Johansson's team named her Lucy. Her species was called Australopithecus afarensis, and she was, for a time, the oldest known member of the hominin family, the group that includes all species more closely related to modern humans than to chimpanzees. She was not human, not by any modern definition, but she was one of us in the broadest and most meaningful sense. She was part of the experiment that would eventually produce humanity. What Lucy tells us, above all else, is that the defining characteristic of the hominin line from its very earliest days was not intelligence, not language, not technology. It was something far simpler and far more radical. It was the decision, encoded not in any individual choice, but in millions of years of natural selection, to stand up. Bipedalism, the ability to walk habitually on two legs, is one of the strangest and most consequential adaptations in the history of vertebrate life on Earth. From a purely engineering standpoint, it is deeply counterintuitive. Four-legged locomotion is more stable, more energetically efficient at high speeds, and less demanding on the spine and lower limbs than two-legged walking. Every other large primate has stuck with four limbs, and they are not obviously wrong to have done so. Gorillas, chimpanzees, and orangutans are all highly successful animals, superbly adapted to their environments. And yet bipedalism opened doors that quadrupedalism kept firmly shut. The most immediate advantage was energetic. Studies comparing the walking efficiency of humans and chimpanzees have shown that human bipedal locomotion is significantly more efficient over long distances than the knuckle-walking gait of chimpanzees. This may seem like a minor point, but in an environment where food is scattered, where resources must be tracked across large territories, where the difference between finding a carcass before a rival group and arriving an hour too late might mean the difference between feeding and starving. Efficiency in travel is enormously important. Early hominins with a more efficient gait could cover more ground, find more food, and survive lean periods that would have broken less mobile competitors. But the deeper advantage was what bipedalism made possible over the longer term. By freeing the hands from the task of locomotion, it set in motion a cascade of anatomical and neurological changes that would eventually transform everything. Hands no longer needed for walking could be used for carrying food, infants, materials. Hands used for carrying could develop greater dexterity. Greater manual dexterity created pressure for better fine motor control, which required changes in the brain. Changes in the brain created new cognitive capacities. New cognitive capacities enabled new behaviors. New behaviors created new selective pressures, and those pressures drove further changes. It was a feedback loop unlike anything the ape lineage had previously experienced, and once it began, it was almost impossible to stop. There is another, less obvious advantage to bipedal locomotion that is often overlooked. Walking upright exposes a smaller surface area to direct overhead sunlight than quadrupedal movement does, and it positions the head and body further from the hot ground, where temperatures can be significantly higher than at head height. In the open savanna environments that early hominins were beginning to exploit, where the sun is fierce and the shade is sparse, this thermal advantage was not trivial. Less heat absorption means less need for water. Less need for water means fewer constraints on how far from a watering hole a group can range. A group that can range further can access more resources. Resources means survival. Combined with the extraordinary cooling efficiency of human sweat glands, we have more sweat glands per unit of body surface area than any other primate, enabling us to thermoregulate during sustained physical activity in ways that most other large mammals cannot. This thermal advantage may have enabled a foraging strategy unique in the animal kingdom: persistence hunting. Rather than overpowering prey with speed or ambush, early hominins may have been able to simply run large animals to exhaustion over many hours in the heat of the day, when the prey could not cool itself fast enough to continue, and the hunter could. Every skilled tracker and long-distance runner in the world today carries, in the structure of their body, the legacy of this strategy. The elongated legs, the stabilizing gluteal muscles, the shock-absorbing arches of the feet. All of these are adaptations not just for walking, but for endurance running, and they represent one of the more elegant solutions to the problem of how a moderately sized, moderately fast primate can successfully compete for access to large animal protein in an open environment. Bipedalism alone did not save us, but it created the platform on which everything else was built. The world into which the earliest hominins walked was not the world we know today. Africa 3 million years ago was warmer and wetter than it is now, though the global cooling trend was already well underway. But the crucial feature of the early hominin environment was its variability. Unlike the stable equatorial forests that remained the home of the other surviving great apes, the African savannas and woodland mosaics that hominins inhabited were dynamic, unpredictable places. Seasons were pronounced. Rainfall fluctuated dramatically from year to year and decade to decade. Droughts struck without warning and lasted for years. Floods followed. The vegetation shifted with the climate, and with it the availability of the foods that hominins depended on. This variability, rather than being simply an obstacle, may actually have been the engine of hominin evolution. The variability selection hypothesis, developed by the paleoanthropologist Richard Potts and his colleagues at the Smithsonian Institution, proposes that it was not any single environmental condition, but rather the repeated, unpredictable swings between different conditions that drove the evolution of the hallmarks of human cognition: flexibility, innovation, the ability to solve novel problems rather than relying on fixed, inherited responses. An animal adapted to one specific environment performs brilliantly in that environment and poorly everywhere else. An animal adapted to deal with unpredictability performs adequately in many environments, and crucially, it can cope when familiar environments vanish. The fossil record seems to support this idea. Periods of rapid climatic fluctuation in African prehistory, detectable in the isotopic composition of lake sediments and marine cores, correlate with periods of rapid evolutionary change in the hominin lineage. New species appear, old species vanish, brain size increases. The toolkit becomes more sophisticated. It is as though the climate was a teacher whose lessons were brutally effective precisely because of their harshness. And so the very instability that drove so many of the Miocene apes to extinction may have been the pressure that forced our own ancestors to become more flexible, more creative, and more generalist than any ape that had preceded them. 2.5 million years ago, something happened that would prove to be a turning point, not just in the story of our lineage, but in the history of life on Earth. A member of the hominin family, probably one of the later Australopithecines, though the exact species remains debated, began producing stone tools. Not just picking up sharp stones and using them opportunistically, as other primates can do, but deliberately flaking one stone against another to produce a cutting edge. The technique is known as Oldowan technology, after the site in Tanzania where the earliest examples were found, and at first glance it appears almost trivially simple. A few blows of one stone against another, producing sharp flakes that could be used to cut meat and scrape marrow from bones. But the implications were anything but trivial. Access to animal fat and protein is enormously valuable for a primate brain that is already beginning to expand. The brain is the most metabolically expensive organ in the mammalian body, consuming roughly 20% of the body's total energy budget, despite representing only 2% of its mass. Feeding a growing brain requires high-quality, calorie-dense food, and meat, particularly the rich marrow inside large animal bones, provided exactly that. Stone tools gave early hominins access to a food source that had previously been almost entirely unavailable to them: the carcasses of large animals. Even as scavengers rather than hunters, early stone tool users could access marrow and meat from animals killed by lions and leopards, following predators to their kills and driving them off long enough to smash the bones. This was not just a dietary innovation. It was the first step in a process by which hominins began, slowly and fitfully, to re-engineer the world to meet their needs, rather than simply adapting their needs to the world. Every other species on Earth was shaped by its environment. Hominins were beginning, with the most primitive and tentative of gestures, to shape their environment instead. The pace of change over the next 2 million years was, by evolutionary standards, breathtaking. The genus Homo, which emerged from the Australopithecine lineage around 2.5 million years ago, showed a progressive increase in brain size, a progressive refinement of stone tool technology, and a progressive expansion of geographic range. Homo habilis, the earliest member of our genus, remained largely confined to Africa. Homo erectus, appearing around 2 million years ago, was the first hominin to leave the continent entirely, spreading across Asia and into Europe, colonizing habitats ranging from tropical forest to the margins of temperate woodland. It was a species of extraordinary duration and tenacity, surviving for nearly 2 million years, longer than any other species of human known to science. And yet Homo erectus, too, eventually vanished. Not through any sudden catastrophe, but through gradual replacement by successor species with slightly larger brains, slightly more sophisticated technologies, and slightly greater behavioral flexibility. The story of the genus Homo is not one of a single triumphant march to modernity. It is a story of branching and extinction, of species appearing and disappearing, of evolutionary experiments that sometimes succeeded and sometimes failed, with the successful ones building on the platform provided by their predecessors. There is a site on the northern shores of Lake Turkana in Kenya called Chesawanja, where, among the sediments of an ancient lakebed, researchers have found fragments of baked clay and charred bone dating to approximately 1.4 million years ago. The interpretation is contested, as it always is with evidence this ancient, but many researchers believe these deposits are the remnants of controlled fire use by early members of the genus Homo. If they are correct, then fire is among the oldest human technologies in the archaeological record, predating complex language, predating symbolic art, predating farming by well over 1 million years. The relationship between fire and human evolution is one of the most profound and underappreciated in all of natural history. Fire is, at its most basic, a technology for extracting more energy from food. Cooking breaks down the cell walls of plant material, making starches and fibers more digestible. It denatures proteins in meat, increasing the efficiency with which the gut can absorb their amino acids. It kills pathogens that would otherwise cause illness. And the net effect of all of these changes is that a cooked meal delivers significantly more usable calories to the body than the same ingredients consumed raw. Studies of raw food diets in modern humans have found that individuals who do not cook their food consistently lose weight regardless of how much they eat, because the human digestive system is no longer capable of extracting sufficient energy from unprocessed foods. We are, in a literal biological sense, adapted to cooked food. We require it. The anthropologist Richard Wrangham has argued, compellingly, though not without controversy, that the adoption of cooking was the single most important event in human evolutionary history, because it freed up the energy needed to power the extraordinarily expensive human brain. A chimpanzee, which does not cook, spends roughly 6 hours a day chewing and processing food just to meet its basic caloric needs. Early hominins who began cooking their food could meet those needs in far less time, freeing hours each day for other activities. Social interaction, tool-making, exploration, the development of the complex cultural practices that increasingly distinguished the hominin lineage from all other apes. Fire also provided warmth and light and protection from predators. Practical advantages whose value in an open, predator-rich environment could hardly be overstated. A fire at the entrance to a shelter kept lions and leopards at a distance and extended the usable hours of the day beyond the limits of sunset. Communities gathered around fires at night were communities in which information could be shared, stories told, relationships maintained and strengthened. The campfire, in this reading, was not just a cooking device and a source of warmth. It was an institution, one of the earliest and most enduring of human social technologies, a place where the bonds that held groups together were forged and renewed night after night, across hundreds of thousands of years. Consider for a moment what the world looked like 300,000 years ago. At this point in time, at least 7 or 8 different species of hominin were alive simultaneously on Earth. In Africa, an archaic population that would eventually give rise to our own species was already beginning to show the distinctive features: the rounded skull, the reduced brow ridge, the pointed chin, that define Homo sapiens anatomically. In Europe, the Neanderthals were a cold-adapted species of exceptional resilience, with brains as large as our own, and a capacity for complex social behavior, symbolic thinking, and technological innovation that we have consistently underestimated. In Asia, a smaller-brained species called Homo erectus clung on in isolated populations in the Far East, while a mysterious group known from their DNA alone, the Denisovans, appear to have ranged across much of the eastern part of the continent. In the islands of Indonesia, a dwarf species called Homo floresiensis had evolved in isolation, its small body and small brain the product of millions of years of island living. On the island of Luzon in the Philippines, an even more recently discovered species called Homo luzonensis left fragmentary but unambiguous evidence of its existence. The world, in other words, was not waiting passively for Homo sapiens. It was full of intelligent, adaptable, tool-using bipedal primates who had been shaped by hundreds of thousands or millions of years of selection in their respective environments. They were not the brutish, simple-minded creatures of early popular imagination. They were our relatives, our contemporaries, in some cases our literal ancestors through interbreeding, and they were genuinely formidable competitors. And yet, within a remarkably short period of time, from the perspective of deep history, all of them were gone. Every single one. The last Neanderthals died out around 40,000 years ago. The last Denisovans, as far as we can tell, disappeared at around the same time. Homo floresiensis survived until roughly 50,000 years ago, perhaps later. The other archaic populations in Africa and Asia faded into the expanding wave of modern human migration. By 30,000 years ago, at the latest, Homo sapiens was the only human species on the planet. How did we do it? What was the decisive advantage? The temptation, when confronting this question, is to reach for a single explanation, a magic ingredient that separated us from all the others. Greater intelligence, better tools, more sophisticated language, a more peaceful disposition, sharper spears. The history of paleoanthropology is littered with confident answers to this question that subsequent evidence has dismantled. Neanderthals, once assumed to have been cognitively inferior to modern humans, have since been shown to have made jewelry, buried their dead with apparent ceremony, created rudimentary cave art, and manufactured tools of considerable sophistication. The assumption that they simply could not compete intellectually with our ancestors no longer holds. The real answer is more interesting, more complex, and in some ways more uncomfortable. The real answer is more interesting, more complex, and in some ways more uncomfortable. Begin with what the Neanderthals actually were, because popular culture has done them a lasting disservice. Discovered in Germany's Neander Valley in 1856, just 3 years before Darwin published On the Origin of Species, Neanderthals were almost immediately cast as the primitive, brutish forebears of modern humanity, stooped, dim-witted, incapable of language or abstract thought, barely distinguishable from the animals around them. This characterization was wrong in virtually every important respect, and the evidence accumulated over the past few decades has demolished it comprehensively. Neanderthals had brains that were, on average, slightly larger than our own. They manufactured complex composite tools, hafting stone points to wooden or bone shafts with carefully prepared adhesives made from birch tar, a process that required both technical sophistication and several sequential steps of planning. They buried their dead, sometimes with flowers, though this specific claim is debated. The evidence for deliberate burial itself is not. They used pigments for body decoration. They created abstract markings in caves that predate the arrival of modern humans in Europe by tens of thousands of years. Recent research has found evidence suggesting they may have had the physical capacity for speech. They cared for their injured and elderly, as shown by skeletons exhibiting healed bones and arthritic degeneration, conditions that could only have been survived with the sustained help of others. These were not primitive creatures. They were people in every meaningful sense. And yet, they are gone. Every Neanderthal who ever lived, every lineage that persisted through hundreds of thousands of years of European winters and repeated glacial advances, every community that gathered around a fire, made a tool, buried a companion, all of them are gone. Their DNA lives on in small fragments in the genomes of most people alive today, a faint genetic echo of the interbreeding that occurred when modern humans first spread into Europe. But Neanderthals as a species, as a coherent biological and cultural entity, ceased to exist around 40,000 years ago. Start with numbers. Modern humans, from a relatively early point in their history, lived in larger social groups than most other hominin species. The reasons for this are debated. Some researchers link it to the development of more complex language, which allowed larger groups to maintain social cohesion. Others point to technological innovations in food storage and preparation that enabled denser, more sedentary populations. Whatever the cause, the effect was significant. Larger populations contain more individuals, and more individuals means more potential for innovation. If a useful new technique or technology appears by chance in a population, as all innovations ultimately do, it is more likely to spread and be retained in a large, well-connected population than in a small, isolated one. Small populations tend to lose knowledge over generations. Large, networked populations accumulate it. This is not merely a theoretical point. Archaeological studies of the complexity of stone toolkits among populations of different sizes have found a striking correlation. Larger, better-connected populations consistently maintained more sophisticated and diverse toolkits than smaller, more isolated ones. The famous example is Tasmania, where Aboriginal peoples, isolated by rising sea levels 10,000 years ago, progressively simplified their toolkit over the following millennia, losing technologies that mainland populations retained. Complexity requires connectivity. Neanderthal populations were consistently smaller and more geographically dispersed than modern human populations in Europe and Western Asia. Their reproductive rate appears to have been somewhat lower. Their social networks, as far as can be determined from the distribution of raw materials used in their tools, appear to have been less extensive. They were not cognitively inferior, but they may have been socially disadvantaged in ways that made the accumulation and transmission of knowledge more difficult. And in an evolutionary arms race where the capacity to innovate and adapt quickly is the decisive variable, a slight disadvantage in social connectivity can translate into a catastrophic disadvantage over thousands of years. But numbers and connectivity alone do not fully explain human success. There is something else, something that shows up in the archaeological record as a subtle but unmistakable shift in the complexity and diversity of material culture, and that shows up in the neurological and genetic literature as a series of changes in the organization of the brain that appear to distinguish modern humans from all preceding species. Call it symbolic cognition. The ability to represent things that are not present, to use a mark on a cave wall to stand for a bison, to use a sequence of sounds to stand for a concept, to think about the past and the future as well as the immediate present, to imagine things that do not exist and then work to bring them into existence. Language, art, religion, planning, all of these depend on symbolic cognition, and all of them appear in the archaeological record in a cluster that coincides, broadly, with the emergence of anatomically and behaviorally modern humans. The oldest known cave paintings, at sites in Spain and Sulawesi, date to at least 45,000 years ago, and possibly much earlier. Ochre pigments used for body decoration and possibly symbolic marking have been found at South African sites more than 100,000 years old. Carefully pierced shell beads, almost certainly used as jewelry, as personal adornment, as signals of identity within a social group, appear across Africa at similarly early dates. The oldest known abstract engravings, geometric patterns incised into ochre blocks, date to around 77,000 years ago at Blombos Cave in South Africa. These objects are not just aesthetically interesting. They are functional evidence of a cognitive revolution that fundamentally altered the nature of the competition between Homo sapiens and every other hominin species on the planet. A species that can represent information symbolically can store and transmit knowledge far more efficiently than one that cannot. Oral traditions, however imperfect, allow accumulated knowledge to persist across generations in ways that purely observational or imitative learning cannot. A group that can tell stories about where to find water in drought years, or how to treat a particular plant to make it edible, or which predators to watch for in a particular landscape, has an enormous survival advantage over a group that must rediscover such knowledge from scratch in every generation. Language in particular, complex, syntactically structured, infinitely generative language, is likely to have been the single most transformative adaptation in hominin evolutionary history. It enabled coordination on a scale impossible for any preceding species. It enabled the transmission of abstract knowledge. It enabled planning over extended time horizons. It enabled the formation of the large, trust-based social coalitions that allowed modern human populations to maintain the social connectivity that was so essential to their survival. And it enabled something else, less tangible but equally important: the ability to create shared fictions, shared beliefs, identities that extended beyond the immediate social group to encompass strangers who had never met but who recognized one another as members of the same tribe, the same community, the same people. This last capacity may seem the most nebulous, but it had concrete and immediate survival value. A group of 20 people, however intelligent and well-equipped, is vulnerable to a group of 200. A species that can coordinate the actions of hundreds or thousands of individuals who do not know each other personally, through shared beliefs, shared rituals, shared symbols of identity, can mount a collective response to threats and opportunities that is simply beyond the reach of species limited to the small, face-to-face social groups of earlier hominins. There is a cave in the Dordogne Valley of southwestern France, set into a limestone cliff above a river that has changed its course multiple times since the cave was first occupied. Inside, the walls are covered with paintings that have survived for 17,000 years. Horses, bison, deer, aurochs, rhinoceros, mammoths, and bears, rendered in ochre and black manganese with a vividness and accuracy that stops even the most jaded modern observer in their tracks. The animals are painted in motion, their legs in stride, their heads turned, their breath almost visible in the cold, underground air. Here and there, human handprints have been blown in pigment around the outlines of their makers' palms, a gesture of presence and identity across 17 millennia. We call this place Lascaux, and it is one of dozens of decorated caves scattered across southwestern France and northern Spain that were painted during the peak of the last ice age, when glaciers covered much of northern Europe and the landscape above the cave was not the mild green farmland it is today, but a cold, wind-swept steppe populated by the animals depicted on the walls. The people who painted these caves were living in one of the harshest environments that Homo sapiens has ever inhabited outside the tropics. They were doing so successfully. They were also apparently doing it beautifully. The Lascaux paintings are sometimes cited as evidence that early modern humans were cognitively fully modern by this point, capable of the same kinds of abstract thinking, aesthetic sensibility, and symbolic representation as any human alive today. But their deeper significance may lie in what they tell us about the social function of art. These caves were not, for the most part, simply homes in which people happened to paint. They were visited over thousands of years by multiple generations. The same sections of wall were repeatedly painted. Some images were modified, updated, or painted over. The caves appear to have been places of gathering, of ceremony, of collective activity, spaces in which the social bonds that held communities together were affirmed, renewed, and communicated across time. Art, in other words, was technology. Not in the narrow sense of a physical tool, but in the broader sense of a means by which humans solved a fundamental problem: how to maintain the social cohesion of large groups across space and time in conditions where the bonds of personal acquaintance were insufficient to hold everything together. The cave paintings of the Dordogne were instruments of community, as practical in their way as a well-made spearhead or a carefully woven basket. The Toba supervolcanic eruption, which took place approximately 74,000 years ago on the island of Sumatra, is thought to have been the largest volcanic event in the last 2 million years. It ejected somewhere between 2,000 and 3,000 cubic kilometers of magma, ash, and gas into the atmosphere, a quantity so enormous that it is difficult to visualize. For comparison, the 1980 eruption of Mount St. Helens, which caused widespread devastation across the northwestern United States and left an indelible mark on the people who witnessed it, involved less than 1 cubic kilometer of material. The Toba eruption plunged the Earth into what researchers call a volcanic winter. Ash and sulfur dioxide in the stratosphere blocked sunlight on a global scale, causing temperatures in some regions to drop by as much as 15 degrees Celsius. The cooling persisted for years. Vegetation across large parts of the tropics and subtropics collapsed. Food chains were disrupted from the ground up. Populations of animals large and small declined sharply, and human populations collapsed too. Genetic evidence, specifically the striking lack of genetic diversity in modern human populations relative to what would be expected from a species of our age, has led a number of researchers to propose that the Toba eruption very nearly extinguished our species entirely. Some estimates suggest that the global population of Homo sapiens may have fallen to as few as 10,000 individuals in the aftermath of the eruption, perhaps fewer. If this is correct, and it remains a subject of active debate, then every human being alive today is descended from an extraordinarily small group of survivors who made it through a global catastrophe of almost unimaginable scale. Other researchers have challenged this interpretation. Archaeological evidence from southern India and East Africa suggests that some human populations continued to function and even thrive during and after the Toba event. The genetic bottleneck may have predated Toba, or it may reflect other factors in early human demographic history. The debate is ongoing, but what is not disputed is the fundamental point. At some stage in the early history of our species, our total population was extremely small. We were briefly, or perhaps repeatedly, a species on the very edge of oblivion. The margin between our survival and our extinction was narrow in a way that is genuinely hard to contemplate. What pulled us through? Almost certainly the same qualities that had driven the success of the hominin lineage from its earliest days: flexibility, social connectivity, and the ability to find new solutions to new problems, rather than clinging to strategies that no longer worked. A species with a narrow ecological niche and a fixed behavioral repertoire cannot survive a global environmental catastrophe. A species capable of rapid behavioral innovation, capable of shifting its diet, its technology, its social organization, its geographic range in response to changing conditions, such a species has a chance. The ice ages themselves, not just the Toba catastrophe, but the entire cyclical pattern of glaciation that has characterized the last 2 million years of Earth's climate history, were among the most severe challenges that early hominins faced. At the peak of the last glacial maximum, around 20,000 years ago, ice sheets extended from the poles to cover much of northern Europe, northern Asia, and North America. Sea levels were more than 100 meters lower than today, connecting land masses that are now separated by ocean. Vast expanses of what is today productive agricultural land were buried under kilometers of ice, and even the regions that remained ice-free were cold, dry, and in many cases poorly vegetated. For populations of archaic hominins already stressed by habitat contraction, increasing competition with modern humans, and the general intensification of climatic variability that characterized the late Pleistocene, these conditions were often insurmountable. Neanderthal populations in Europe and Western Asia experienced repeated contractions during cold periods, retreating to southern refugia and then re-expanding during warmer intervals. Each contraction reduced their numbers and eroded the genetic and cultural diversity that was their greatest adaptive asset. Each re-expansion began from a smaller base than the one before. Modern human populations faced the same challenges, but they had tools, literally and figuratively, that other hominins lacked. Sewn clothing, which required both needles and the conceptual understanding of how to join pieces of material together, allowed populations to survive in environments far colder than any preceding hominin had inhabited. Constructed shelters, supplemented with animal hides and heated with fire, extended the habitable zone into regions that would have been inaccessible to earlier species. Stored food, preserved by drying or freezing, buffered communities against the seasonal and interannual fluctuations in resource availability that had so often proven fatal to smaller, less technologically sophisticated populations. And the bow, the spear thrower, the fish trap, the snare, technologies for extending human reach over prey animals without requiring the close physical proximity that made hunting so dangerous, dramatically increased the efficiency with which modern humans could exploit whatever food resources were available. A hunter with a spear thrower could kill an animal from twice the distance possible with a hand-thrown spear. A community with fish traps could harvest protein from rivers and lakes with a consistency and volume impossible for any earlier technology. These innovations were not individually decisive, but their cumulative effect was to make modern human foragers substantially more productive per unit of effort than any preceding hominin species, and that productivity advantage translated directly into larger, healthier, more reproductively successful populations. In the highlands of Papua New Guinea, at an elevation of more than 1,000 meters above sea level, there is an archaeological site called Cook Swamp, where the evidence for one of the most consequential transitions in human history is preserved in the sediments of an ancient marsh. Beginning roughly 10,000 years ago, though some researchers suggest the beginnings may go back further, the people of this region were deliberately manipulating the landscape to encourage the growth of food plants, draining the marsh, digging channels, mounding the earth, clearing the forest. In short, they were farming. Agriculture was not invented at Cook Swamp alone. Within a few thousand years of the end of the last ice age, plant and animal domestication appears independently in at least a dozen locations around the world. Wheat and barley in the Fertile Crescent, rice and millet in China, maize and squash in Mesoamerica, sorghum and finger millet in Africa, potatoes and quinoa in the Andes. The transition from foraging to farming was not a single event, but a global pattern driven by the convergence of several factors: the end of the glacial period and the stabilization of the climate into the relatively mild, predictable conditions of the Holocene. The depletion of large animal populations in many regions, partly by hunting and partly by habitat change, making foraging increasingly difficult, and a positive feedback loop by which growing human populations created incentive to produce more food from the same area of land, which in turn supported even larger populations. Agriculture transformed human existence in ways that are still playing out today. It enabled population growth on a scale impossible for foragers, ultimately increasing the global human population by orders of magnitude. It enabled the accumulation of surplus food, which made it possible to support specialists, craftspeople, priests, administrators, soldiers, who did not produce their own food. It enabled the construction of permanent settlements and eventually cities, which concentrated populations in ways that accelerated the exchange of ideas and the development of new technologies. It enabled, in time, writing, mathematics, organized religion, long-distance trade, and all the complex institutions of civilization. But it also introduced new vulnerabilities. Farming populations were dependent on a small number of crop species and susceptible to harvest failure on a scale that foraging communities, with their far more diverse and flexible resource base, rarely experienced. They were vulnerable to new infectious diseases, partly because of the high population densities that agriculture produced, and partly because of close proximity to domesticated animals, which served as reservoirs for pathogens capable of jumping to humans. They were susceptible to social inequalities and political structures that concentrated wealth and power in ways that foraging societies largely avoided. And yet the farming pathway led, eventually, to here, to a species of 8 billion individuals spread across every continent, manipulating the global environment on a scale without precedent in the history of life on Earth. Whether this represents ultimate triumph or the setup for a new kind of extinction crisis is, perhaps, the central question of our time. Around 60,000 years ago, A small group of modern humans, perhaps no more than a few hundred individuals, possibly fewer, crossed from the Horn of Africa into what is now Yemen and began the colonization of the rest of the world. We know this from genetics. Every non-African human alive today is descended from this single founding population, and the genetic diversity of non-African populations is strikingly lower than that of African ones, a signature of the severe demographic bottleneck that the dispersal represents. The ancestors of every European, every Asian, every Native American, every Pacific Islander, every Australian Aboriginal person trace their ancestry back to those few hundred individuals who made the crossing at the southern end of the Red Sea. What drove them to make that crossing? We cannot know. Perhaps resource competition within Africa was already beginning to intensify as modern human populations grew. Perhaps climate changes were altering the landscapes of the Horn of Africa in ways that pushed populations outward. Perhaps there was simply a group, curious, mobile, following the coast and its reliable food resources, that kept going further than any of its predecessors had thought to go. Whatever the reason, the dispersal, once begun, was rapid by any standard. Within a few thousand years of the initial crossing, modern humans had reached the Indian subcontinent and Southeast Asia. By 50,000 years ago, they were in Australia, crossing a body of open water that required either intentional navigation or an extraordinary stroke of luck. By 40,000 years ago, they were in Europe, encountering and ultimately replacing the Neanderthal populations that had occupied the continent for hundreds of thousands of years. By 15,000 years ago, at the latest, they had crossed into the Americas and begun the final phase of their global colonization. Whatever the reason, the dispersal, once begun, was rapid by any standard. Within a few thousand years of the initial crossing, modern humans had reached the Indian subcontinent and Southeast Asia. By 50,000 years ago, they were in Australia, crossing a body of open water that required either intentional navigation or an extraordinary stroke of luck. By 40,000 years ago, they were in Europe, encountering and ultimately replacing the Neanderthal populations that had occupied the continent for hundreds of thousands of years. By 15,000 years ago, at the latest, they had crossed into the Americas and begun the final phase of their global colonization. The speed of this expansion is not fully explained by population pressure alone. There is something in it that speaks to a deep characteristic of the hominin temperament, a restlessness, a curiosity, an orientation toward the horizon that seems to have been present from the very earliest stages of our species' history. Homo erectus had already demonstrated this quality, crossing open water to reach the island of Flores 1 million years ago, and leaving unmistakable traces of its presence in the most remote corners of the Old World. But modern humans took it to a qualitatively different level. They were not just moving along coastlines and following river valleys. They were actively navigating, planning multi-day or multi-week journeys across open water, identifying and memorizing star patterns to guide them, building watercraft capable of sustaining communities through the crossing. The settlement of the Pacific Islands, the last major region of the globe to be colonized, is perhaps the most astonishing example. Beginning around 3,500 years ago, a seafaring culture we now call the Lapita people began spreading out from the islands of near Oceania into the vast blue emptiness of the Central Pacific. Using outrigger canoes equipped with sails, navigating by the stars, the movement of ocean swells, the behavior of birds, and a sophisticated body of knowledge accumulated over generations of open ocean sailing. They island hopped across thousands of kilometers of open water to reach Tonga, Samoa, the Cook Islands, and ultimately, by around 1,000 years ago, Hawaii to the north, New Zealand to the southwest, and Easter Island to the east. No other species has ever colonized an environment in this way. It is, by any measure, one of the most extraordinary feats of exploration and adaptation in the history of life on Earth. At each stage of this expansion, modern humans encountered environments utterly unlike the African landscapes in which their species had evolved. Arctic tundra, tropical rainforest, high-altitude plateaus, coastal deserts, temperate woodlands, Pacific islands separated by thousands of kilometers of open ocean. Each of these environments presented unique challenges, required unique adaptations, and drove the development of unique technologies and cultural practices. The ability of a single species to successfully colonize all of these radically different environments within a geological eye blink was and remains almost unprecedented in the history of life on Earth. It was possible only because of the combination of qualities that had been building in the hominin lineage for millions of years. Bipedalism, which freed the hands and set in motion the cascade of cognitive changes that followed. Brain expansion, driven by the relentless pressure of a variable, unpredictable environment. Social complexity, which allowed the accumulation and transmission of knowledge across generations. Symbolic cognition, which enabled language, planning, art, and the cultural technologies that extended human adaptive capacity far beyond anything possible through biological evolution alone. And a generalist flexibility, inherited from ancestors who had survived the collapse of the Miocene forests, precisely because they were not too narrowly specialized to cope with change. Sit for a moment with the improbability of it. The line of descent from the last common ancestor of chimpanzees and humans to a modern Homo sapiens is 6 or 7 million years long. Along that line, species appeared and vanished at a rate that makes clear just how easily the whole enterprise could have ended at any point. Sahelanthropus chadensis, the earliest possible hominin, lived on the shores of a lake that no longer exists in a landscape utterly transformed. Australopithecus afarensis, Lucy's species, survived for nearly 1 million years before going extinct. Homo habilis, Homo ergaster, Homo heidelbergensis all appeared, thrived for a time, and disappeared. Paranthropus, the robust side branch of the hominin family, lasted for over 1 million years before vanishing. Each of these extinctions was, at the time, complete and permanent. Each represented the end of a unique evolutionary experiment. Each erased from the world a form of life that would never exist again. And yet across the whole of that 6 million year journey, something, a thread, a lineage, a succession of improbable survivors, kept going. When forests contracted, hominins walked out into the open. When climates shifted, hominins shifted their behavior. When prey became scarce, hominins invented new technologies to find and exploit it. When populations were decimated by volcano or drought or plague, the survivors rebuilt. This is not a story of inevitable triumph. At every step, extinction was a genuine possibility. At some stages, the Toba bottleneck, the hardships of the last glacial maximum, the repeated range contractions of early modern human populations in Africa. It was closer than comfortable. The margin between our existence and our non-existence has been, at various points, a matter of thousands of individuals, perhaps hundreds, choosing correctly or simply getting lucky at moments when the cost of error was everything. It is worth pausing here to acknowledge something that is easy to forget in a narrative of success: the species that did not make it. Gigantopithecus, the largest primate that ever lived, survived into the Pleistocene, possibly until just 200,000 years ago, sharing a world with our own ancestors. Its extinction was not dramatic. It was slow. Its bamboo forests contracted, season by season, over thousands of years. Its food supply dwindled, its populations fragmented. Individual animals traveled further and found less. Breeding rates fell. Populations that had been large enough to be demographically stable shrank below the threshold at which stochastic variation, bad luck in plain terms, could not be absorbed. One by one, the isolated remnant populations of this magnificent creature vanished without witnesses, without record, without mourners. The Neanderthals died more recently and more closely in our shadow. We have their DNA. We have their tools, their pigments, their ornaments. We have the bones of their dead, sometimes carefully placed, sometimes sprinkled with ochre, in what looks from this distance uncomfortably like grief. They were people, in any reasonable sense of the word. They had faces and voices and families and knowledge passed down through generations. They made decisions. They suffered losses. They probably wondered, in whatever cognitive idiom was available to them, about the big questions. And then, over perhaps 10,000 years, they were gone. Not killed in any single battle or catastrophe, but outcompeted, outnumbered, absorbed in small part into our own lineage, and ultimately eclipsed by a related species that happened to reproduce slightly faster, maintain slightly larger social networks, and generate slightly more technological innovation per generation. There is something in this that demands more than scientific detachment. The story of human survival is also, and inescapably, the story of other extinctions. We did not survive in isolation. We survived in competition, and our success was at least partly the cause of others' failure. This is not unique to our species. Competitive exclusion is a fundamental principle of ecology, but it is uniquely difficult to contemplate when the species in question were people. The story does not end with the emergence of civilization. It does not end with the agricultural revolution, or the Bronze Age, or the great empires, or the industrial transformation of the 19th century. We are still, in the deepest sense, the products of the same evolutionary pressures that shaped the hominins of the African savanna. Our brains are the same brains that were shaped by the variable, unpredictable environments of the late Pleistocene. Our social instincts were calibrated in communities of a few dozen to a few hundred people, and they are sometimes badly matched to the demands of nations and global civilizations. Our appetites, our biases, our capacity for both extraordinary cooperation and extraordinary violence. All of these are legacies of the long evolutionary journey that brought us here. And the challenges are not over. Our species has survived volcanic winters, ice ages, epidemic diseases, and the extinction of every other hominin lineage. But we now live in a world in which the climate is changing faster than it has changed in millions of years, And this time the driver is not an asteroid or a supervolcano, but ourselves. We live in a world in which the biological diversity that has been the font of evolutionary resilience for over 3 billion years is being eroded at a rate that recalls the great mass extinctions of deep time. We live in a world in which the technological capabilities that saved us so many times are now capable, for the first time in the history of life on Earth, of posing an existential threat to the species that created them. In this context, the story of how we survived is not merely history. It is a reminder of what survival actually requires: flexibility rather than rigidity, generalism rather than over-specialization, social connectivity rather than fragmentation, the willingness to innovate rather than to cling to strategies that worked in the past but may not work in the future. Every quality that kept our ancestors alive through the Miocene collapse, through the bottleneck of near extinction, through the ice ages and the volcanic winters and the competition with our closest relatives, all of these qualities are still available to us. Whether we choose to use them is, as it always has been, the decisive question. There is a phrase that recurs in the scientific literature on extinction: background rate. It describes the normal, expected pace at which species disappear from the planet in the absence of any extraordinary disruption. Roughly 1 species per million per year, a slow and steady attrition driven by the ordinary processes of competition, climate variation, and ecological change. We exist against this background. The hominin lineage has been running against it for 6 million years, losing species after species to it, and yet always managing to keep one step ahead. Sahelanthropus, Ardipithecus, the Australopithecines, Paranthropus, Homo habilis, Homo erectus, Homo heidelbergensis, the Neanderthals, the Denisovans, all have contributed to the current of evolutionary heritage that flows through us. All have fallen away behind us, and yet something endures. The question of whether that something endures for another 1,000,000 years or another 10,000 is one that no paleontologist, no geneticist, no evolutionary biologist can answer. It depends on choices that have not yet been made, on technologies that have not yet been invented or deployed, on social and political decisions whose outcomes are genuinely uncertain. But the deep history of our lineage offers at least one clear message. The species that survived were the ones that changed when changing was necessary. They were not the strongest, not always the smartest in any narrow sense, not the most technologically sophisticated at any given moment. They were the most adaptable. They were the ones willing to abandon what was no longer working and to try something new. We carry all of them within us. Every extinct hominin species that left descendants, every ancient Miocene ape whose lineage persisted through the Great Collapse, every individual human being who made a slightly better choice in a moment of crisis and lived to pass that advantage on, all of them have contributed, through the long cumulative logic of natural selection, to who and what we are now. We are not separate from our evolutionary history. We are its current expression, and the qualities that carried our ancestors through every crisis this planet has thrown at them for millions of years are still present in us, waiting to be called upon. That is, perhaps, the most important thing the story of how we survived has to tell us. Not that we are special in any absolute sense. Other lineages have shown extraordinary resilience, extraordinary adaptability, extraordinary capacity to endure. But that we are here at all is evidence of something remarkable in the nature of this particular experiment, and that we are here at a moment when the choices we make will determine whether the experiment continues, is both a privilege and a responsibility that our ancestors, who fought so hard and so long to give it to us, surely deserve to have taken seriously. There is a moment in every good survival story where the outcome is still uncertain, where the protagonist has the tools and the knowledge and the capacity to succeed, but has not yet made the choices that will determine whether they do. We are living in that moment now. The hominin lineage has survived for 6 million years by adapting to change, by finding new solutions to new problems, by maintaining the social and technological flexibility that allowed it to thrive in environments utterly unlike those in which its ancestors evolved. That capacity is still there. It is in every human brain, in every human community, in the accumulated knowledge of every culture and civilization that has ever existed on this planet. The story of how we avoided extinction is not finished. It is still being written in laboratories and legislatures and village councils and family kitchens and schoolrooms and council chambers, by 8 billion descendants of a few hundred individuals who crossed a narrow stretch of water 60,000 years ago, who were themselves the descendants of Australopithecines, who stood up in a shrinking forest and walked out into the open 5 million years before that. We are, all of us, the product of the improbable. We are here because our ancestors were flexible enough, connected enough, innovative enough, and sometimes simply lucky enough to survive conditions that extinguished every other species in our family. That inheritance is remarkable. What we do with it is up to us. The story of human survival is not finished. It is still being written in laboratories and legislatures and village councils and family kitchens and schoolrooms and council chambers, by 8 billion descendants of a few hundred individuals who crossed a narrow stretch of water 60,000 years ago, who were themselves the descendants of Australopithecines, who stood up in a shrinking forest and walked out into the open 5 million years before that. Think about what that lineage has already survived. Toba and its volcanic winter, the Miocene collapse and the loss of dozens of ape species, the repeated glacial advances that compressed habitable land into refugia that could barely sustain the populations sheltering in them, the diseases that swept through the dense, newly sedentary communities of the Neolithic and killed without warning or pattern, the famines that followed crop failures in a world newly dependent on a handful of cultivated plants, the extinctions of every other species in our genus, one by one, leaving us uniquely alone on a planet that was once shared with beings who understood the world in ways we can now only guess at. We are here despite all of that, because of all of that, in a sense, because every one of those challenges selected, generation by generation, for the qualities that define us at our best: the willingness to learn, the capacity to cooperate, the ability to change when change is necessary. The small female on the African plateau turns her face back into the wind. The group moves on. The story continues. You have been watching How We Avoided Extinction. If you enjoyed this video, please like and subscribe and leave us a comment to tell us what you thought. We will see you next time.